Okay, so welcome to you for this NPTEL course on electroceramics. My name is Ashish Garg and I am an associate professor at the Department of Material Science and Engineering at IIT Kanpur. So before we go for formal lecturing, I'll just give you a brief introduction of the course, why this course is important. So in this lecture, I'm going to give you the introduction about the course and some review of the fundamentals of things like structures and bonding in materials, which form the basis of structures of these kind of materials. So why electroceramics are important? Because electroceramics are important because they are used in many technological applications like in sensors, actuators, various kind of transducers devices. They can also be used, they are also used for storage devices like fuel cells and batteries, and even for data storage, and many optical devices are made from these materials as well. Broadly speaking, there are you can define these differentiate these ceramics in electronic ceramics, optical ceramics and magnetic ceramics. However, the fundamentals of these ceramic materials are closely related to each other. So these are the so technological importance of these materials make it important to understand their fundamentals, such as structure, the defect chemistry, how can we tailor the properties. So these are important aspects to understand these materials. Some of the examples you can take, for example, silicon oxide, which is a dielectric, well known dielectric. It's used as a data storage element in your memories like random access memories. Materials like barium titanate or lead titanate are used as sensors and actuators. They are also called as ferroelectric materials. Oxides such as iron oxides, which are basically magnetic in nature, are used for data storage in magnetic heads. Materials like, for example, zinc oxide, they are used as materials to protect the circuit, and they are also called as devices called as varistors. And materials like zirconium oxide, which are stabilized with other oxides. So we will see how this stabilization is done in the course, but these are used in applications like fuel cells and batteries, which are nothing but storage applications. So these are some of the examples of technologically important applications where these typically you see that most of these are oxides, although some of them can be carbides, etc. And this explains the importance of electroceramics in technological applications and why we need to study them. And they are also used in bulk form, thin film form, depending upon the requirement, and both of these forms require very good understanding of fundamentals of these materials. Now, in order to understand this course properly, you need to know basics of structure of materials, thermodynamics and solid state physics. I have recommended some books in the bibliography of this course, which I will show you in a couple of slides. But you need to know these topics because I am not going to go through these topics in detail, and this course is very well suited for final year undergraduates of most discipline. Typically I would say it's really it would be quite easy for or quite well suited for undergraduates from material science, physics or chemistry. However, other disciplines can also do that, and also for fresh graduate students, those who have taken just admission into master's courses. List of topics that we will cover in this course are we will first very briefly review the bonding and structures in materials. So, I will just devote maybe 1 or 2 lectures on this topic because this forms the basis of the next topic, which is the structure of ceramic materials, which is quite an important topic because the structure of ceramic materials is indeed formed on certain basis, and this is where you need to know a little bit about the bonding and structures. And then we will move on to structure of ceramic materials, which are again different kind of structures depending upon what kind of elements they contain, and we look at basis first of all, how the structures are formed, and then we will look at the various different kind of structures. And the third topic would be defects chemistry and equilibrium. So we will look at how the defects are formed in various ceramic materials, and we will look at bit of thermodynamics of them. And then we will move on to more applied topic, which is well, fundamental applied in some sense both. We look at how these defects which are formed in various materials diffuse and form the basis for conduction in ceramics, which is actually a quite an important topic. And then we will look at the properties of these some of these electroceramic materials. So, we will first look at linear and nonlinear dielectric ceramics, and then we will look at magnetic ceramic materials, and then couple of lectures on optical ceramics, and then some special electroceramics which are not included in previous categories such as multiferroics and superconductors. And then finally, we will look at very briefly on preparation methods for both bulk and thin films, because these oxides have to be formed in such manner so that they are useful in device forms, and that is where preparation is important. Total number of lectures that we will devote to this course is about between 42 and 45. That will depend how we go in the course. Bibliography, this is so the books which are on top in red, they are very important books for this course. So, the first one is Physical Ceramics by Chiang, Burney and Kingery, and the second one is Principles of Electronic Ceramics by Hench and West, and the third one is an Introduction to Ceramics. It's really a classic book by Kingery, Bowen and Ullman. And then you can also go through Electroceramics by Moulson and Herbert. This is a good book from the point of view of applications in processing, and while previous three talk mostly about the fundamentals and properties, and this bottom book is basically non-stoichiometry, diffusion and electrical conductivity in binary metal oxides. Although it talks about binary metal oxides, this is a good book from the point of view of understanding defect chemistry and equilibrium. Other books are supplementary books. Solid state physics, you can go through, for example, Kittel, Solid state physics, which is a very classic book on solid state physics, and then Electronic properties of materials by Soliman and Walsh, Solid state physics by Ashcroft and Mermin, Solid state physics by Decker. Any of these books is good enough to give you a good understanding of solid state physics. And then there are some other books, specialized books, for example, Transition Metal Oxides by Cox, and then C.N.R. Rao and Raviu have also written a book on transition metal oxides, emphasizing on the structure, properties and synthesis of these materials. And then some other books like Basic Solid State Chemistry, Non-Stoichiometric Oxides, Feynman Lectures on Physics. These are really good actually. I mean, for fundamentals of physics, they are really good books. And then for basic material science, you can refer to Material Science Engineering by Raghavan or Material Science Engineering by Callister. So, I guess the books in the blue, or as it looks black, are mostly supplementary books if you want to enhance your understanding of certain things which you don't know before, but the top 5 books are actually really directly useful from the point of view of this course. So, so this is about the introduction. Now, I will give you a brief overview of structure and bonding in these materials. So, first we will go through a review of structures. Now, in the structure we all often talk about lattice. Now, what is a lattice? Now, we do not start with atoms directly, we start with other points, distribution of points in space. So, points can be distributed in space in a haphazard manner as shown on the left, or in an ordered manner as shown on the right. Now, the ordered distribution of points in the space forms a lattice which is called as a point lattice, where you have a periodic distribution of points and each point has identical neighborhood. In contrast, if you look on the left, no two points have similar neighborhood. So, no two points have similar neighborhood, and as a result it is not called as a periodic lattice. So, in summary, you can say a point lattice is basically you have a regular arrangement of points with identical neighborhood, periodic, and each point has a identical neighborhood, and if you do not have that, it is not a point lattice. So, for example, you can have now even if you have that definition, let us say this is a periodic pattern, right. It looks like a periodic pattern, where what I have done is I have put hexagons together with points denoted as circles at the corners of hexagons. Now, if you look at now a cursory look tells you in most cases that it is a periodic structure. However, if you compare point A and point B, point A has 3 neighbors, point B also has 3 nearest neighbors, that is fine, but the arrangement of nearest neighbors around point A is not similar to that of point B. Point A has 2 neighbors on the right and 1 on the left, while B has 2 on the left and 1 on the right. As a result, this is not a point lattice. On the other hand, if I modify a little bit by putting another point in the center of each of the hexagon, then I see that both point A and point B have identical neighborhood, number of neighbors as well as the pattern of neighbors is similar. Hence, this is a point lattice. So, I hope you understand the concept of point lattice. Now, in the lattice, in the point lattice, the smallest repeatable unit is called as a unit cell. So, in this 2-dimensional picture, I can make a parallelogram by connecting these 4 points, and this would be called as a unit cell. Now, you can see the choice of unit cell is not unique. You can make a unit cell like this, you can also make a unit cell like this. So, choice of the unit cell is not unique, but all of these unit cells which contain only 4 points at their corners will have same area, and the dimensions of this unit cell, in this case you have A in this direction, B in this direction, and the angle between A and B is gamma, and these 3 parameters are called as unit cell parameters. In the 3 dimension, it would look something like this. This is for example, a cube. It does not need to be a cube, it could be anything, it could be a cuboid, but the point is the translation from one point to another in x direction will be called as A, and in the y direction it would be B, and in the z direction it would be C, and the angles alpha, beta, gamma between AB, BC or CA would be all these 6 will make as lattice parameters. So, AB gamma would be lattice parameter for 2D structure, ABC and alpha, beta, gamma would be lattice parameters for a 3D structure. As I said, the choice of unit cell is not unique, you must remember that. So, the question now arises, how many choices are possible? Well, we can have many choices, but we can define some of these choices into certain systems which will form the later which will form basis of later what we will see as crystal systems. Now, so far we have been talking about the point lattice. Now, if you replace these points by certain objects in the lattice, what it makes is a crystal structure. So, combination of what is called as motif, which is let us say an atom or a group of atoms or a formula unit, and the point lattice makes a crystal structure. So, for instance, in this top left picture, you have these little blue atoms, which is a single atom. I have replaced each point with this blue atom, and then I can draw a unit cell. Now, do not worry about the shape, because shape could be anything. So, this is a unit cell. This is called as a crystal structure, a smallest unit of crystal structure consisting of 1 atom per unit cell in this picture on the right. Okay, so this is basically your point lattice. So, in this point lattice, I have replaced each point by, for example, this kind of motif, which is nothing but a black or gray circle. Now, when I do that, I get the same pattern as on the left, but with each point replaced by this sphere or circle, gray circle. So, this will be a crystal structure consisting of these gray atoms, and each unit cell will contain only 1 atom. Similarly, if instead of taking 1 gray atom, if I take a group of 2 atoms, I can put them in any way I want, but that would not make a periodic lattice necessarily. So, what I have to do is that I have to put this group of atoms in an identical fashion at each and every point. So, for instance, if you look, this group of atom is pointing upwards here, replacing, for example, this point. So, all other group of atoms are replacing all other points in the identical fashion, and this again makes a periodic lattice. So, I can connect, for instance, these corners, and this makes again a lattice, a crystal lattice consisting of 1 gray and 1 blue atom. Now, one gray and one blue is, you can consider it as a group of atom or a formula. So, this would be more true about, for example, for a metal or single element material. This would be true for a multi element or a compound. Similarly, instead of 2 atoms, a compound can have 3 atoms, and again you replace each of these points by 3 of these atoms, making sure they are all oriented in one direction, and each unit cell consists of one formula unit. So, if I again connect these, this will contain one formula unit. So, one red, one blue and one gray atom. So, motif, you can define it as a unit or pattern, and if you combine this with point lattice, it will make a crystal structure. Now, the unit cell, the lattice can be your primitive lattice or a non-primitive lattice. So far we have seen only primitive lattices, where each of these squares, as you see in the red here on the left. So, the first one, the most basic is this, where you connect the corner of each of these atoms. So, if you look at this, no matter where you put this red square, it will always contain only one unit. So, if it is at this position, it has 4 gray atoms at the corners and 2 blue atom at the center of these edges, this which will be shared by 2 neighbors. So, 4 divided by 4 will be 1, and 2 divided by 2 will be 1. So, 1 plus 1. So, group of 2 atoms. No matter, now you can change the position of this square. I can change the position of the square in such a manner, it will still contain a group of atoms. So, this will be called as a primitive lattice. Primitive lattice would be a lattice which a primitive unit cell is a unit cell which contains only one formula unit or single unit of motif. It could be a single atom for a single elemental material, or it could be a formula unit for a compound. Now, if you look at this green box, this green box is slightly bigger, and if you now count, it contains 2 gray atoms and 2 blue atoms. It contains 2 formula units. So, this is called as a non-primitive lattice. Since it contains 2 formula units, the area of this unit cell is exactly twice to that of the primitive unit cell. So, this is called as a non-primitive unit cell. So, a motif in this case is, this is your blue. I think this has moved a little bit in the PowerPoint. Don't worry about that. Now, another consideration in forming crystal systems and Bavais lattices is concept of symmetry. Symmetry is basically an operation which brings any object back to its original configuration, and there are 4 basic symmetry operations. The first one is called as reflection about a plane in a unit cell. So, here what happens is, basically you create a plane in the middle of this unit cell, and the point M1, for example, in this case, across the plane on the left is reflected by another identical point on the right, which is M2. So, it is like looking at yourself in the mirror. So, mirror plane is mirror plane is nothing but reflection across about a plane. So, here M1 is reflecting to M2, and second one is rotation. Rotation is, if you rotate a point about a certain axis by a certain angle, the configuration that it achieves after rotation is identical to the previous configuration. So, for example, if you take a cube, this is the most simplest case. You can have, for example, I start with point M1. So, for 4-fold rotation, you can have this point M1 going to M2, right. Just consider, now what will be the 4-fold rotation? This is a cube. If I put the line that you see, this line, this is the line which is going through the center of the face of the cube to the other opposite center of the face, penetrating through the cube, and if you rotate around it by 90 degrees, this point M1 will move to point M2, and if all these points were identical, you can say that the position at this point, you can say the look of lattice in this position is identical to the look of the lattice when the point M1 goes to M2. So, it does not change the configuration of the lattice. So, this is your 4-fold rotation. 3-fold rotation would be the rotation in which you rotate by 120 degree. So, basically if you say n fold, what it would be equivalent to is that 2 pi divided by n. So, for 4-fold, n will be 4, this will give rise to 90 degree rotation. For 3-fold, 2 pi divided by 3, and that would give rise to 120 degrees, and so on and so forth. So, threefold would be along the body diagonal of this cube. So, the point M1 will become M3, keeping the configuration of the lattice similar. Similarly, you can have a twofold axis as well. Twofold would be the face diagonal. So, you connect basically an axis, connect this point and rotate around this axis. So, that point M1 will become M4, and this will be twofold rotation. So, any of these three operations, if you perform, the configuration of lattice does not change. So, your so this is fourfold, this is threefold, and twofold will be 2 pi divided by 2 would be 180 degrees. You can also have sixfold, which is nothing but 60 degrees rotation, and that is possible in, for example, in hexagonal case. If you have a hexagon, now it is up to you. I will leave it to you to show that why do you not have fivefold and sevenfold rotations. Third one is inversion center. So, inversion center is basically the point M1 becomes M2. So, this is across the body diagonal. Your inversion center would be somewhere here. So, point M1 would look, so whether you look at point M1 or M2, the configuration of the lattice would be same across this center of inversion. And now, finally, you will have rotation inversion center, where M1 becomes first M1 prime due to fourfold rotation along this axis, and this M1 prime will then become M2 if it was followed by an inversion across this center. So, this would be rotation inversion. So, these are four basic symmetry operations. There are many more symmetry operations which we are not going to details of this, but if you combine these symmetry operations with the previous definitions of lattice, then we come to crystal systems. We have said that choice of unit cell is not unique, but you cannot have infinite combinations. So, because it would be hard to remember. So, what people did was they divided these unit cells based on certain criterias into 7 crystal systems to make our life easier. The first one is simple cubic, which is where A is equal to B is equal to C and alpha, beta, gamma are equal to 90 degrees, and the minimum symmetry element for this is a 4. It has 4 threefold rotation axis, which is along the body diagonals. Similarly, you can also, now the second combination would be A is equal to B, but not equal to C, but all three angles are equal to 90 degrees. This will make a tetragonal structure. So, here the C parameter is different from A and B, and this must have a fourfold rotation or rotation inversion axis, which would be along, fourfold rotation would be along your parallel to the C axis, going through the center of this face and center of the bottom face. And the third one would be your orthorhombic crystal, where A is not equal to B is not equal to C, and alpha, beta, gamma all three are equal to 90 degrees. So, it is an orthogonal system with unequal lattice parameters, lattice translation parameters, not the angles. So, this must have 3 perpendicular twofold rotations or rotation inversion axes. So, these are 3 crystal systems. We will have 4 more. Fourth one is rhombohedral, which is where A is equal to B is equal to C, alpha, beta, gamma are equal, but not equal to 90 degrees. So, this is the different, this is the deviation from a cubic crystal, and this must have a threefold rotation axis. Similarly, now number 5 is hexagonal. Here A is equal to B is not equal to C, alpha, beta are equal to 90 degrees, gamma is equal to 120 degrees, and this must have a 6-fold rotation axis. Remember, I talked about 6-fold rotation, which is by 60 degrees around a certain axis. And 2 more, 6th one is monoclinic. This is so basically we are increasing the level of difficulty. So, here A is not equal to B is not equal to C, and alpha is equal to gamma is equal to 90 degree is not equal to beta. So, alpha, gamma are equal to 90 degrees, but beta is different, and this must have a 2-fold rotation axis. And 7th is the triclinic, which is the most difficult one, but not the most common one. Triclinic has it has all three A, B, C are different in this structure, and alpha, beta, gamma are all different, and none of them is equal to 90 degree as well. And this doesn't have a minimum symmetry, any minimum symmetry element. This is most unsymmetrical structure. And based on, and these crystal systems can further be classified into Bravais lattices. There are 14 kind of Bravais lattices. So a cubic structure can further be divided into simple cubic structure, as we have learnt, a body centered cubic structure which has an extra atom at the center of the unit cell, and a face centered cubic structure where atoms occupy the center of the 6 faces. So naturally, as you can see, body centered and face centered structures are non-primitive structures, and simple cubic is a primitive structure. So primitive is always defined as P, and non-primitive body centered is defined as I, and face centered is defined as F. This is useful in writing space groups, which we will not consider in this course, for the definition of crystals. Similarly, tetragonal is defined as you have two variations. One is simple tetragonal, which is primitive. Another is body centered tetragonal, which is non-primitive, where an atom is sitting at the center of the unit cell. Now you can ask questions, why don't you have other variations of face centered cubic, face centered why don't you have other variations of tetragonal lattice? That is because if you have other variations, you can always reduce them to one of the existing 14 Bravais lattices. Similarly, orthorhombic, you have simple orthorhombic, body centered orthorhombic, base centered orthorhombic, and face centered orthorhombic. So these are the 4 variations of orthorhombic. One is primitive and 3 are non-primitive. In case of rhombohedral, there is no other variation, it is only rhombohedral. Hexagonal does not have any variation as well. So you only have primitive lattices in case of rhombohedral and hexagonal, although rhombohedral is referred as R in case of crystallographic notations. And monoclinic has simple monoclinic, and it also has a base centered monoclinic defined as C. And in triclinic, you have only one variation, which is primitive triclinic. So you have total of 14 Bravais lattices. If you want to learn the details about how these Bravais lattices are formed and what is the basis, you need to learn a bit more about crystallography, and you can read any crystallography book, or you can go to the NPTEL course on the structure of materials. That would be useful to enhance the understanding of structures. Now, crystals are often defined by planes and directions. Now, these planes are nothing but crystallographic planes are nothing but identification of various faces as seen on the crystal. They are defined by indices such as HKL, either in the round brackets or in curled brackets. Round brackets would define one plane, and curled brackets would define identical set of planes, and these HKLs are nothing but integers, and these are called as Miller indices. And crystallographically, you can define a plane in a crystal by this equation, where H by A x plus K by B, sorry, it should be y, and L by C z is equal to 1, where H by A plus and K by B and C by L are the intercepts on of the plane on whatever the plane is on x, y and z axis. A, B, C are the unit cell lengths. Similarly, you can define directions. Basically, they are atomic directions in a crystal along, so you can say they are vectors basically, and they are also defined by units such as UVW, or in the square brackets, or in the smaller brackets UVW for an identical set of directions. The only difference with respect to vectors is that vectors can go out of the crystal. Directions are usually depicted inside the crystal from one side to another, but they are nothing but vectors fundamentally. So, for example, a plane in a crystal would be 110, this would be 110 plane. So, 110, what you have here is the intercept on x axis is 1. So, this would be 1 by 1, intercept on y is 1, again 1 by 1, and there is no intercept along 0 along the z axis. So, intercept along the z would be 1 divided by, so you can say it is infinity, intercept is infinity, and then you take reciprocal of these to get the plane digit. Similarly, if you want to draw 111, 111 would be intercept 1 on x, 1 on z, 1 on y, and if you connect all these 3 points together, you will make 111. And similarly, you can make anything like 200. 200 would be intercept on x would be 1 by 2, intercept on y would be 1 by 0, intercept on x z would be 1 by 0. So, there is no intercept on y and z, which means it is parallel to y and z, and it cuts x on half a distance. So, this plane would be your 200 plane. Often you encounter negative digits as well. For example, you can have bar 111. Bar 1 is nothing but it is a matter of shifting the center. So, in case of x, instead of taking the center here, you take the center here. So, your x so you always travel in x in this direction, y remains positive, z remains positive. So, bar is handled by just shifting the center. Similarly, directions, 111 direction is nothing but you travel from this point, one in x direction, one in y direction, and one in z direction, and combine these 2 points, this will make a 111 direction. If you want to draw 100 direction, 100 would be this direction. Similarly, if you want to draw 1 bar 20, for bar 20 you need to again change the axis. So, bar 2 is along the y direction. So, instead of choosing the point center here origin, I can shift the origin here. So, what I do is that basically I go half along x, minus 1 along y, and 0 along z. So, half along x, minus 1 along y, and I connect these 2 points. So, if I connect these 2 points, this would be 1 bar 2 0 direction. I have you can use 1 bar 2 0 as well, but you need to go out of the crystal. So, that is why I took a fraction. So, basically the largest digit is converted into 1 and all other digits become fractions to depict the direction in a unit cell. So, now we move on to bonding. Basically materials have two kinds of bondings, one is primary and one is secondary. There are 3 primary bonding mechanisms: metallic bonding, covalent bonding, and ionic bonding. And secondary bonding is often referred as van der Waals bonding, and there are other kind of secondary bonds as well, which we will not go into much details, but it is just that for the review purposes. So, metallic bonding, basically you have these atoms around which you have this gas of or sea of electrons which are free to roam around, and this is why metals are very malleable and conducting. And metals like nickel, iron, copper, gold, silver, etc., they show this kind of covalent bonding. It's typically due to sharing of electrons. For instance, in methane, you can have 1 carbon atom surrounded by 4 hydrogen atoms, and so 1 electron. So, each electron of carbon is shared by each of these hydrogen atom. In case of diamond, you can have 4 electrons of each carbon atom is shared by 4 electron of another carbon atom to make it to fulfill the sharing requirements, or to satisfy their periodic, to satisfy the electronic arrangement to fill the orbitals. And the examples of these materials can be mostly group 4 elements like carbon, silicon, germanium, and materials like silicon carbide, or even gases like methane, and as well as glasses like silicon oxide. They have predominantly covalent bonding character. And then ionic bonding. Ionic bonding is basically due to large differences in the electronegativities of 2 ions. So, for example, you can have materials like sodium chloride or magnesium oxide. Cation has, for example, in this case +1 charge, and anion has -1 charge. So, each of these, both of them are either ready to give or accept the electron. So, they have very strong affinity towards each other. So, sodium and chlorine, for example, in this case sodium gives 1 electron to chlorine, which readily accepts it, and so this is basically a very strong bond which is formed between 2 ions, 2 differently charged ions. And This kind of bonding typically have very high bond energy. I am not going to fundamentals of bond energy. If you want to go through that, you need to go to any basic book, for example, Kittel or Raghavan or Callister. So bond energy is basically a parameter which decides how strong the bond is. Typically high bond energy will imply high bond strength, which typically implies high modulus, brittle nature of materials, and in general low thermal and electrical conductivity, which makes these materials very good insulators. And most of the electroceramics have very large proportion of them are ionically bonded compounds. So this is what is going to govern the formation of structures in many of these compounds. And finally, you have secondary bonding. Secondary bonding can be due to asymmetric electron clouds. So as a result, you have fluctuating dipoles, and these fluctuating dipoles lead to attraction of the ends of these entities, and which leads to kind of attraction between them. So this is secondary bond. You can also have a permanent dipole moment in the molecules, which also gives rise to kind of attraction between two oppositely charged ends. So these are two kinds of secondary bonding which happens in most materials. Secondary bonding is very prevalent in materials like polymers. So polymers have a chain which is covalently bonded. So in the chain they have along. So here you have covalent bonding along the chain. So for example, it could be a chain of ethylene in this, but between the chain, between the chain you have secondary bonding, which is the van der Waals bonding. So as a result, polymers are strong along the chain, but they are flexible because of secondary bonding between the chains. So chains can they can entangle with each other and give rise to low modulus and high flexibility in polymers typically. So this is a basic review of structure and bonding in these materials. Now we will look at how the atoms in various structures pack against each other. So the next topic in this lecture would be to see if you have atoms, then what are the possible fashions in which, if you put these atoms in a space, in which they can pack together. What is and then we will concentrate on what sort of voids are there in between these atoms, which can be then filled by various other kind of atoms which are crucial in forming the ceramic structures. So earlier we saw that how the structure of what the fundamentals of structures, the concept of lattice, crystal systems, etc., and then we looked at the kind of different bondings. Just to emphasize, most of these ceramic materials are bonded by covalent or ionic bonding, typically ionic with some covalent character, and due to differences in the bond energies, the covalent ionically bonded materials tend to be more stronger. They have high modulus, typically low electrical and thermal conductivity, and are brittle in nature. And on the other hand, covalent bonding tends to be again reasonably stronger, sometimes not as strong as ionically bond, but it tends to be very directional in nature. So for instance, the hybridization of orbitals requires this bonding, the bonding to be directional. As a result, the bonds are stronger than metallically bonded material, and metallically bonded materials typically are malleable, conducting, and very easy to deform either at room temperature or high temperatures. And then secondary bonding is typically a weaker kind of bonding, such as van der Waals bonding. Now we will see how the atoms, if you consider atom as a hard sphere, how these atoms pack themselves in the space. So there are three ways in which they can do. There are many, there are various ways in which atoms can pack themselves in the structure. The first, so we can say packing of atoms. Now, the first simple way of packing these atoms is in the way like this. So you have an atom like this, you have an atom like this. So this is the first layer of atoms, okay, And what I do is that if I put another layer of atom, I can put another layer of atom right on top of it. So, the second layer will have same configuration as this and it goes right on top of it. So, in the 3D what you make is something called as a cube, if all of these atoms were of same size and same type. So, what they make is a cube, and corner of these cubes are occupied by each atom. This is called as a simple cubic structure with all atoms at 0, 0 and 0. Second way of packing these atoms could be, you again take a layer. This is the first layer configuration. Second layer is shifted by, if you look at in this direction, in this picture, second layer, first atom is like this, and then second atom would be, so if the atom center of first atom is here, the second atom center would be here, and third atom center would be here. So, this is little bit shifted, right. So, since you have this kind of configuration, so the first layer is this one, this is the second layer, and the third layer goes right on top of first layer. So, this would be 1 and 3. So, when you make a 3D structure like this, so what you have is the body centered cubic structure, where corners are occupied by these spheres. All the spheres are identical, mind you, and so these are, so this is, so first and third layer make the simple cube, and the second layer goes inside this. I have put a dash just to differentiate, otherwise these two are same. So, this will make a body centered cubic structure, and atomic position would be 0, 0, 0 and half, half, half. You can calculate the packing factor. Packing factor is nothing but volume of all atoms divided by volume of the cell, and you can work it out yourself. It would be 0.52 for simple cubic structure and 0.68 for BCC structure. I will leave it to you to work it out. It is very simple exercise. All you need to do is that you consider the radius of each atom as r, and make sure and assume that all the atoms are touching each other, and so you can determine what is the packing factor. The third way in which atoms can pack with each other is formation of close packed structures. So, this is a close packing of atoms. In this kind of structure, you have first row of atoms like this. This is the closest possible packing in 2D. Spheres can pack only in this manner. The second layer which comes, it can go right on top of this, but that will not be close packing. But the second layer, you can put one atom here, another here and another here. Now, so these are all empty sites. So, it can do like this, or it could have gone here, it does not matter, all are identical. So, if I just change the color, so you have these sites and you have these sites. So, this is the first layer. Okay. The second layer can go either on top of these or on top of these. All of them cannot be filled simultaneously because size of the atoms would not allow that. Now, the second layer would be, let us say I choose to fill this one, second layer would be like this. So, this would be second layer. Let us say this I call it as A layer and this I call as B layer. Now, the next, and this can continue. So, all the red type empty sites will be covered by the second layer. Now, the third layer which can come, it can come either right on top of A layer, which means if I put the third layer, it can go in this fashion. So, this would be my third layer going on right on top of the first layer, or the third layer can go in different fashion. Third layer can cover the sides which were not filled previously. So, the third layer can go now on top of these. Right. So, this layer has completely different orientation as compared to rest of two layers. So, this will be called as ABC kind of stacking. So, this ABC kind of stacking gives rise to what is called as a face centered cubic structure. Or FCC, or often called as cubic closed, CUBIC, cubic closed packing. Or CCP. So, what it looks like in a cubic form is like this. You have a cube, corner of cubes are filled, and center of all these 6 faces are filled as well. This will make a cubic closed pack structures. All in this schematic, I have not made each atom touch each other, but in this kind of configuration, closed packing, they will be touching each other. So, so this ABC stacking leads to this kind of configuration, and the plane of visualization of ABC stacking is basically the 111 plane of FCC unit cell. Okay. And so, you have to basically stack ABC layers along on top of 111 plane, and if you had this AB kind of stacking, AB would be something like, so you have first layer, second layer would be this layer, and the third layer would again be the same as first layer. So, this would be A, this would be B. So, this is ABC, and if you have AB, this would lead to something called as hexagonal structure or hexagonal closed packed. Structure called as HCP packing. So, you put another one on top, and so if you put another one on top, it would become just like A, and the unit cell, the smallest unit cell for a hexagon is, if you connect the center of these and go in the Z direction, it would look something like this. And one atom will be at the center. So, this would be A layer, this would be B layer, this would be again A layer. So, these all will be at 0 0 0, and this would be at 1 by 3, 2 by 3, half, or 2 by 3, 1 by 3 half, depending upon the way you look at it. So, this would be your hexagonal close packed structure. You can also calculate the packing factor. Packing factor for these, since these are the most close packed structures, these have a packing factor of about, packing factor would be 0.74. Since only the stacking sequence is difference, there is no other difference in terms of filling the voids or putting atoms on top of each other, because the number of nearest neighbors either in this structure or that structure both is 12. Packing factor remains same. So, only the sequence changes, but not the packing factor. So, this is the closest possible packing possible from only one type of spherical atoms. Now, once you have seen these various kind of atoms packing possible, the next thing is you still see some voids inside these structures, right. So, no matter how closely you pack, you can only pack 74% of the space, 26% of the space is still empty, and these spaces are often called as voids or interstices. Some of these voids can be filled by the foreign atoms, and that is why they are called as interstices. These are called as interstices, and the atoms which fill these voids are called as interstitial atoms, and it is a very common phenomenon in most of the materials. For example, steel. In steel, iron makes the BCC lattice and carbon goes to the interstitial sites. There are typically two kind of interstitial sites. One is tetrahedral interstitial site, second is octahedral interstitial site. Tetrahedral interstitial site is the site which contains 4 nearest neighbors around the interstitial atom, whereas octahedral interstitial site is the body looks like a octahedra, and the interstitial hole has 6 nearest neighbor around it. So, we will look at the interstitial sites in the next class, and then we will move on to the materials which ceramic materials which are which can be formed by various kind of bonding such as ionically or covalently bonded materials. Thank you.